Hello everyone. My name is Stela Silva. I am a NASA postdoctoral fellow at NASA Goddard. And I know some of you know of my work of machine learning that I have developed with Greg Omshenk and Richard Berry. This work is coming, trying to have a paper this year on this. But today I'm going to take this as an opportunity to talk about a different task that I had the opportunity to be doing. So this work was carried out by me, by John Hopeck. He's a PhD student at Catholic University. And this is part of the task that we are doing with the Microlensing Modeling Group of the Roman Galactic Exoplanet Survey project infrastructure team. So this group of event modeling is led by Dave Bennett and Valerio Bosa. And I want to talk about the inclusion or omission of the motion in planetary microlensing models. So let's give some context. So we are excited. Rome is being launched next year. For more information, there's going to be a whole session about Rome tomorrow morning. And we are very, very excited because we are expecting about 1,400 microlensing bound planets. And this is a lot, this is like 7 times more the amount of microlensing planets that we have. But you know what they say, with great power comes great responsibilities. So Roman have some science requirements. I will not read them in detail, so if you're curious, you can carefully read them later. But I want to point out a word that shows up a lot, which is the word mass. So with the exception of mass ratio on the bottom, they are really talking about mass. And if you're familiar with exoplanet microlensing modeling, you know that the Leica gives us the mass ratio. So the title of this slide already gives a bit of a spoiler. Even though the Leica modeling gives us the mass ratio, there is a way that we can get the mass if we have parallax. So, you do some calculation here, and if you have parallax, then you could get the mass. So, annual parallax have been successfully used to obtain the mass. But we also think that sometimes just considering parallax might not be enough. We might need some higher order effects. So the question here, the talk of today will focus a bit more on parallax. The question is how accurate are parallax measurements and if our lens static models are sufficient. So, well, lens static models, they work pretty well, but sometimes they don't. So this was information that David Bender gave us in our RGES-PIT meeting, that 27% of the events from the Suzuki 2016 sample and 38% of the events with mass measurements, they needed optomotion to be included in the modeling to explain the observational data. So, this is very remarkable to think about it. But we are also talking about microlensing. So this is 6 events. Quick note, one of the events is going to be presented right after this talk. So, 38% is a lot. But why optomotion is affecting the image. So just a quick review of optomotion of the lens system. Usually we don't consider optomotion because we're thinking of cold planets, of really large orbits. They are really far from the host star, so it might be neglectable. But even if it's not very perceptible, the optomotion, it's acting some way because it rotates the binary axis, and which changes the source trajectory angle. And it also changed the project binary separation. So sometimes this is neglectable, but it's happening. So the big question is, how does the non-inclusion or inclusion of motion in the modeling affect the accuracy of parallax measurements and consequently the precision of the planet mass determination? So we want to know what is the fraction of events that are being the need of the motion that will benefit from motion being included, and what if should we just include motion everything, but is including motion everything affecting the parallax measurements of the events that don't have strong motion signal? So that's the question. But how do we answer this question? Well, we need data that we know the answer, and we need to model it and compare, model with motion, model without motion. So we are using the data that was simulated from the team simulation. So this is a representative sample that has 2,000 icons. The method I'm using RT model because it's an automatic method that's well known in the community, and it's a lot of data. So we're using the NASA supercomputers to run the model. We did the modeling of the 2,000 simulated icons, but for this analysis we are gonna use a cut of delta chi-square of 500. So what are we finding so far? So this is preliminary results, and I wanted to see as more like qualitative or something to give some intuition. And the reason why I'm highlighting this preliminary is just because I am using the parallax from the light curve modeling, but I'm not using theta E from the light curve modeling. I'm still using the answer for now. I will still implement. And the other reasons that when we were doing the analysis, we saw that there were a few cases that the best model was a binary star model when it should be planetary. So even though I can manually go choosing a couple and adjust, ideally, we want a systematic way to guarantee that we are choosing the mass ratio. So keep in mind that the mass ratio was overestimated, so this will contribute from the that I'm going to show. So I calculated the planet mass, and then I calculated the relative error, and then I'm going to show you the cumulative distribution. So these are the same plots, just that the one on the left it's a log scale, and the one on the right is a linear scale, and I also did a zoom, so we can see closer. So we can see here that, again, this is preliminary results. The results might be a bit better, but we can show here that the inclusion of the motion might improve the relative error. But I still need to do more work to conclude how much this will be the improvement. So I still have a lot of work to do, like me, John, and the modeling group. So we want to expand the effort and model a couple more simulations. Do this with a rigorous method for deriving planet masses using all parameters from the simulation analysis. Correct events that they are favoring binary star over planetary one. Implement research for small mass ratio events. Implement MCMC for events of interest so we can have better error estimates. And then performs analysis, making the cut for the different masses that are in the science requirements. So a lot of work to be done, but the takeaway of today is, well, parallax are needed for mass measurements. 38% of real events, when I say real events, just in comparison with the simulation, they also needed motion in the modeling. And based on the simulation so far, it's the conclusion of the motion might help determine the mass with more precision. So that's my opinion.
Thanks very much. I was just wondering if you have used any model selection techniques in case that orbital motion and parallax are degenerate, so that you avoid overfitting and interpreting events where you not ambiguously determine the orbital motion parameters.
Yep, so I have not, so far I only ran like RT model direct and all those events, so I mean, this is something that, yeah, I have to think about and try to.
So can you say what impact might be for, say, a demographic study where you ignore parallax to try and improve mass measurements? On an individual level, I can see that it will help. But if, given that demographic studies are presumably going to be very difficult to do at this level for large numbers of events, do you have a feel for how wrong the tomography you could get as a result of it?
So I don't have a number, but if it's parallax, so parallax is what help us get the mass measurement. So if we ignore the parallax, then we can end up with some degeneracies. So I think they've presented some plot that had kind of like the solutions of like theta E crossing here, and well, maybe pi E crossing here, theta E crossing here. So this would help to define the mass. So
Orbital motion?
Oh, for optomotion, yes. So for optomotion, I still, that's what I'm trying to get the numbers. Thank you.
Thank you. Great work and very interesting problem. I have a question about your simulated light curves. So could you tell a little bit more about your cadence and precision? Are they meant to resemble Roman or any other real life survey?
Yes, yeah, I should have said that. That's a good question. Yes, so they are to resemble Roman. They have 3 bands, W146, Z078, sorry, I don't remember exact numbers, and the K1. So the cadence is supposed to be the same as Roman, etc. So this is simulation was done by Matthew Penny's group, the same that did the simulations for the previous penny plot work.
So I wanted to point out there's actually more work to do than you mentioned. However, this is also an invitation to any of you in the audience who would like to help. So one thing we would like to get also, if we could get from these simulations, is ways to determine which events for which orbital motion will be necessary to get accurate parallax measurements, and maybe which events for which maybe we don't need to analyze orbital motion. So if we can get that, that would help us streamline our.
Thank you.
And so anyone who has some ideas on this, you're welcome to join us in trying to solve this problem. And please let me know.
Do you have a typical precision you get on the parallax with or without the motion for Roman light curves?
So I don't know by heart, but I do have some plots that I can show you after, if it works.